take any two points in this plane, they can only be connected by one single line. The solution is limited and finite. If we convert this plane into a sphere and now try to connect the same 2 points, this can now be done using infinite number of lines. But being infinite, strangely, does not mean limitless. In this three-dimensional probability space, even if there are infinite solutions, these can be represented by finite boundaries. This is what I like to call limited infinity. Personally, this concept of limited infinity has helped me try to unite two of the most incompatible theories of all of science intuitively: certainty and uncertainty. And by all of science, I mean all of science. In physics, reality appears probabilistic at one scale and deterministic at another. In biology, inherited versus acquired adaptation. In study of mind, conscious choice versus probabilistic subconscious processes. Even in philosophy, fate and free will, I find these different versions of the same argument, and being a curious person just trying to come up with intuitive models helps me understand reality. This model of limited infinity is a personal thought model to help unify concepts of certainty and uncertainty. To explain this model, I'll follow this map. And the starting point of this map is the history of living world, evolution. This is an ancient organism, Canthomyrix, who lived in this world many years ago. After 16 million years, it evolved into a giraffe. At first glance, this change evolution appears directional. This is what Lamarck thought. Over time, organisms seem to move towards forms that work better. He proposed that organisms passed down traits they need, but this could not explain many observations. Darwin didn't focus on why organisms change, but he introduced a fundamental idea: selection. Nature selects those that are fit and others go extinct. Survival of the fittest. After that, Mendel's experiment led to the discovery of genes, and then sudden random changes in genes, mutations, were identified as the source of change that Darwin had missed. Modern evolutionary theory is amalgamation of these two views, not unification. Mutation is random, selection is not, and their combination is what gives us direction. So this concept of selection is extremely important because this might be a key for unification. Darwin defines selection as constraint and fitness of individual as trait that helps to overcome this constraint. If we take predator versus prey, for a predator, prey is a major constraint. For the prey, predator is a major constraint. Predator's fitness is determined by traits such as sharper claw, big muscles, larger teeth. Prey's fitness is determined by defensive horns, ability to run, hide, and so on. Survival of each side depends on outcompeting the other. So, constraint/selection seems to be a fundamental concept in survival. But notice, when these two sides, predator versus prey, meet, the win is not absolute in level of which side has won, but rather a function of which individual win. So the fitness of a species is an emergent result of highly competitive individuals trying to win against opposite side. Further down, that winning individual may have had such high survival drive because extreme amount of neurochemical for competitiveness. Again, this might be because of unique combinations of synthesis proteins originating from best combinations of genes. Finally, some individuals may have developed unique new random proteins that emerge due to mutations of genes and are more efficient in energy usage to do the same task, thus giving the entire lineup an advantage. Deepest down the pit, availability of energy acts as a fundamental constraint of this universe. So, fitness at any level is jumping over the fundamental constraint, surpassing energy availability in the most efficient way possible. This fitness leads to survival, and survival leads to the passage of genes to another generation, resulting into filtering out of continuously inefficient genes. My next question, can we test this with a simulation to see whether constraints in our model truly drive direction in an uncertain system? Yes. I can't wait to show you what I have in coming episode. But for now, let's move on to next spot on the map. This model resonates with an important modern theory that explains randomness and direction through signal and noise, information theory. The heart of information theory says the information is defined by reduction of uncertainty. As we'll see in the simulation in coming episode, emergence of direction does not come from choice, but instead defined by a constraint. When information is passed, there is a mixture of signal and noise. We don't decode the signal by choosing the correct signal. Instead, we design a decoder which is just a constraint. All the information passes through this decoder, and whichever is not compatible is not taken. Which is compatible is taken as signal. The important point here is direction emerges not from choice, but from removing all the incompatible information. Direction is the byproduct of elimination. Now, with all this in mind, let's go back to our model, which is best represented by this visual. Imagine a node. When considering just this node, how many lines can you draw through this node? The answer is obvious, infinite. But now, another detail is this is a curved surface. The answer is still infinite. but the infinity can now be given a structure and saved by strangely a constraint that is limited. This model intuitively allows infinity uncertainty to exist in the limited space of certainty, and that's what this is about. Next, we test this with a simulation.